Okay, we're continuing our exploration of section 8.5. This time we're going to use a PDF that's given to us to find the probability of an observable event and investigate different probability models. So this is kind of motivated by my personal expertise in mathematical statistics, but also in seeing some applications that come up in your different fields of study that have to do with probability. So the first model that we'll explore is the exponential distributions, which we'll think of a random variable that represents time until something occurs. So maybe time until a phone call ends, neutrino detection at the core of the Earth, the planet. So anything that happens one at a time and occurs independently of each other can be said to have a Poisson process. And in the Poisson process, if we're waiting until the next event occurs, then we're representing a random variable with a exponential distribution. So sometimes that will be written x is distributed as an exponential distribution with lambda as its parameter. And so here it has a PDF f of t equals 0 if t is negative. So we don't care about negative time. On the other hand, if t is positive, then the PDF is lambda times e to the minus lambda t. So this is really an exponential function that's decaying. And it looks something like this. Where at its peak, right, so its highest value is at 0, and that's going to give us the value 1 over lambda, sorry, not 1 over lambda, lambda. And it slowly decays down to 0. So notice that the limit as t goes to infinity is 0, which really represents the fact that the longer you wait, the less likely it is that this event. So it's more likely that it'll happen sooner rather than later, is the idea. So first we should check, is this a PDF? So 1, we can pretty clearly see that for all t, I'm sorry, that's not plug in 0. Well, it's all non-negative, so that's fine. That's not a problem. In this case, all we care about is the fact that f is going to be non-negative. So that's fine. That's not an issue. 2, we just need to check that the integral from 0 to infinity f of t dt is going to be equal to 1. So we're going to evaluate this improper integral. The integral from 0 to b, limit as b goes to infinity, of lambda e to the negative lambda t dt. The antiderivative of that is going to be lambda times negative 1 over lambda e to the negative lambda t from 0 to b. And that gives us the limit from b to infinity of negative e to the negative lambda b plus e to the 0. And notice that this goes to 0. This is literally the number 1. And so we end up with 1. Okay, so this works. All right. Now we can use this to find probability. So we know that if we have this model has parameter lambda, then, and I'm going to claim that 1 over lambda is the mean of. So in terms of mean, what we mean is literally the average. Okay, so we'll make this precise in a later video, which we'll talk about in considerable detail. But we're going to suppose a light bulb has a mean lifetime of 1,000 hours. So this is our example for this model. What is the probability that a randomly selected light bulb has a lifetime less than 1,000 hours? Okay, so in other words, we have here the randomly selected light bulb's lifetime is a random variable that is distributed approximately as an exponential distribution with parameter 0.001. So 1 over 1,000. Okay. Because if the mean is 1,000, then that means that it was 1 over lambda. So the lambda itself is 0.0001. Okay. Then we're asking for the probability that this random variable takes on a value less than 1,000, which is going to be the integral from 0 to 1,000 of lambda e to the negative lambda t. So 0.001 to negative 0.001 t dt. And now we integrate. So antiderivative is negative e to the negative 0.001 t, evaluated at 0 and 1,000. This gives us negative e to the negative 1 plus e to the 0. This is the same as 1 minus 1 over e. And that is technically the answer, but if we wanted to figure out approximately what this is, we're looking at 0.6321, so 63% roughly. Okay. Now, so those are the exponential distributions. Let's talk about another family of distributions that's exciting, and actually extremely common and important it underpins basically everything in statistics. So the normal distributions. These are all families of distributions, by the way. They depend on some parameters that represent different random variables that have different limiting factors, right? So when we're talking about normal distributions, they come up in a lot of different scenarios. So we're typically thinking about something that's called a Gaussian pattern of random phenomena, or bell curve shaped probability density. So when we talk about the bell curve, this is what we're talking about. Okay, so we say x is normally distributed with a mean mu and a standard deviation sigma. Okay, so these are the parameters of the distribution. and it has a PDF phi of x is equal to 1 over sigma of square root of 2 pi e to the negative x minus mu squared over 2 phi squared. Or sorry, not phi, sigma squared. Okay, so this looks roughly like this. I could have drawn a better bell curve, sorry about that, but at the peak, the mean, okay, and then one standard deviation away from the mean is roughly 66% of the whole distribution. So in a higher probability course, not in Stat 300, although we do talk about it briefly in Stat 300, we talk about something called the empirical rule. And so data that roughly fits a bell curve, you can figure out how much fits in between a range of 1 standard deviation of the mean, 2 standard deviations of the mean, and so on. But, so the important thing is that this is a PDF that's symmetric about the line x equals mu. And through some advanced calculus, we can verify that indeed the entire support, so all observable outcomes are ranged between negative infinity to infinity. And this integral, improper integral, is equal to 1. Okay, so to find probabilities, we need values of phi of x, capital Phi of x, is equal to the integral from negative infinity to x of 1 over sigma square root of 2 pi times e to the negative, I'm going to use a different letter variable, t minus mu squared of 2 sigma squared dt. Notice that this is an integral valued function, and it has no elementary function form, okay? So we always needed technology or tables or numerical integration in order to figure out probabilities using this this function directly. And in general, we call this function the cumulative density function. So cool stuff, huh? Beyond the scope of our course right now to talk about this in any further detail, but in the next video then we talk about defining the mean or the expected value of a continuous random variable.